Hey, what's good, bro?
Did you do the project?
Oh, so good.
Hello, everyone. Welcome to my math project presentation. And today I'll be presenting how does horsepower really impact acceleration. And this is by Sierra Lantello and Phoenix Harris. All right, for the introduction, this data set will compare the difference in power between horsepower and basic acceleration. This should help us understand that horsepower is way faster than basic acceleration. This data we will discuss vehicle types, indicating types of vehicles, as in like electrical, sedans, SUVs, trucks. Horsepower shows the power output of the vehicle's engine. Acceleration describes the time it takes for the vehicle to go from 0 to 60 miles per hour. And the fuel types indicates whether the vehicle uses gasoline, diesel, or electric power. And the weight gives the weight of the vehicle in pounds. Vehicles that will be shown in this data is the Chevrolet Malibu. It goes 130 horsepower with 12 seconds to 0 to 60 miles per hour. It takes gasoline and is 3,504 pounds. Next up, we got the BMW 335D. It has 265 horsepower. It takes 5.7 seconds to go 0 to 60 miles per hour. It is a diesel car, and it weighs at 3,825 pounds. Next up, we got the Model S Plaid. It goes 1,020 horsepower. It practically takes 2 seconds to go 0 to 60 miles per hour, and it's an electric vehicle, and it weighs at 4,766 pounds. And finally, we get the Dodge Challenger SE. It has 170 horsepower with 10 seconds to go 0 to 60 miles per hour. It takes gasoline and is 3,770 pounds. And on the right is all the cars. The top left one is the Chevrolet. The top right one is the BMW. The bottom left is the Tesla. And the bottom right is the Dodge. Here's my 5-number summary. Horsepower. Most cars in the data set falls below 453.75 horsepower, with the Tesla model being a significant outlier. And for acceleration, we got acceleration times are skewed towards times, with the Tesla model again as an extreme outlier due to its remarkable performance. On the right side, for horsepower, minimum is 130, and then 25% is 160. Medium is 217.5. 75% is 453.75, and the maximum is the Tesla, which is 1,020. For acceleration, we have the minimum at 1.99 seconds. 25% is 4.77 seconds. Medium is 7.85 seconds. 75% is 10.5 seconds, and maximum is 12 seconds. All right, next up, we get the box plot. This data set is highly skewed in both horsepower and acceleration to the Tesla, which represents the cutting edge electric vehicles technology. The car shows relatively modest horsepower and acceleration, consistent with older or non-performance focused models. Yeah. All right, this is my histogram for the horsepower. Horsepower is the measurement of power output of an energy. Looking at this graph, one can observe that the Tesla model has the highest horsepower with 1,020 horsepower, meaning it has the most powerful engine among these cars. The lowest horsepower is contributed by the Chevrolet Malibu with a horsepower of 130, which is the least powerful engine in between the BMW 335D and the Dodge Challenger, delivering with 265 and 170 horsepower, respectively. All right, here's my histogram for acceleration. Acceleration values have represented in time in seconds it takes for each car to go from 0 to 60 miles per hour. The Malibu low horsepower correlates with slower acceleration. BMW higher horsepower results in faster acceleration compared to the Malibu. The Tesla extremely high horsepower leads to the fastest acceleration time among these cars, the Dodge has moderately low horsepower, results in slower acceleration through it's slightly better than the Malibu. And that's just comparing from this graph, the acceleration histogram, to the horsepower histogram. But anyways, the higher horsepower usually promises faster acceleration time. The Tesla model with the highest horsepower has the fastest acceleration, while the Chevrolet Malibu has the slowest and has the lowest horsepower. This comparison shows clearly how the directly performance of the car concerning acceleration is related to its engine power. So here's my 2 sample t-tests. By running the code, this is what I get. The sample t-test indicates that there is no significant evidence to conclude that the mean of the dataset differ from 0, while the sample mean is 201.8363. Alright, now we're at chi-square test horsepower. The Tesla model stands out with its high horsepower, which is significantly different from the expected values. Other cars like the BMW Dodge show smaller deviation. And acceleration, the Tesla has extremely low acceleration time, 1.99 seconds, which is far below its expected value of 18.79 seconds. Gasoline vehicles, such as the Dodge and the Chevrolet, demonstrates relatively consistent acceleration times near expected values. And on the right is my chi-square test. This is what I get when I run the code. Alright, here's my scatter plot. The scatter plot displays the relations between horsepower, x-axis, and acceleration, y-axis, for 4 cars. Malibu position near lower left with horsepower of 130 and a slower acceleration at 12 seconds. BMW found middle left with 265 horsepower, slightly quicker acceleration. The Tesla found very low right with 1020 horsepower and an insane acceleration with 2 seconds. And it clears both categories. And the Dodge, located near the Chevrolet and the BMW, with 170 horsepower with a 10 seconds acceleration time. Here's my ANOVA testing. The time it took for each variable significantly. By using ANOVA test, I compared the average acceleration time and found that at least one vehicle performs different from the others. This analysis helps us understand which vehicle's acceleration is faster, which can be important information for potential buyers. It conducted a study to see how different types of vehicles compares in terms of acceleration from 0 to 60 miles per hour. I used 4 vehicles: the Chevy, BMW 335D, the Tesla model, and the Dodge Challenger. Just add them all, divide by 4, and you get 7.4225 seconds. Here are my source on the programming from Art Studio, from just everything that helped me get this work done. Yeah. Oh, .in. Yeah, .in.